What happened in the Cretaceous? Today, we dive into the final act of the dinosaurs' reign. The world has changed. Continents are drifting apart, flowers are taking over the landscapes, and dinosaurs are reaching peaks of diversity. Tyrannosaurs, Triceratops, Velociraptors. It's the zenith of an empire over 100 million years old. Yet behind this splendor, a silent threat lurks. Because in the distance, a catastrophe looms. A sudden, unpredictable, and global end. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you, and enjoy the journey. Imagine yourself on the brink of an extraordinary journey through time, 145 million years ago. We are going to explore the last period of the Mesozoic, the Cretaceous, which extends to 66 million years ago. Before entering this fascinating past, it is important to understand what specifically characterizes this era. This brief overview sets the essential framework to better grasp the significant events of this period, representing the last grand chapter of the era of dinosaurs and other extraordinary creatures. When we talk about the Cretaceous, we are referring to a geological time interval. Earth's history is divided into eras, which are themselves split into periods, epochs, and then stages. The Mesozoic, the central era, lies between the Paleozoic and the Cenozoic. The Cretaceous, the last period of the Mesozoic after the Triassic and the Jurassic, is characterized by a reorganization of the continents, a greenhouse-like climate, incredible biological diversity, and significant geological upheavals. Before the Cretaceous, most of the emerged lands formed a supercontinent known as Pangaea. Over time, this mass fragmented into separate continents, and by the Cretaceous, this separation was nearly complete. The tectonic plates continued their slow drift, creating new ocean basins. Among the major openings, the South Atlantic Ocean expanded, connecting Africa to South America. At the same time, mid-ocean ridges were actively shaping the sea floors, giving the oceans a unique geography. In the Cretaceous, sea levels reached unprecedented heights for the Mesozoic era. This phenomenon is explained by intense tectonic activity and the formation of underwater ridges, true bulges on the ocean floor, which globally raised the sea level. These high seas invaded vast continental regions, forming large inland seas where lands far from coasts exist today. Thus, many lands were submerged under warm, shallow waters, fostering remarkable marine biodiversity. Now, let's talk about the greenhouse climate. This term describes a period when the planet's average temperature was much higher than today, and the polar ice caps, if they existed, were very reduced or even absent. During the Cretaceous, the climate was therefore warm and humid, with heat better distributed towards high latitudes. In other words, the temperature difference between the equator and the polar regions was less marked than today. How do we know this? Scientists analyze markers in rocks and fossils, like the isotopic composition of oxygen in certain shells, which helps estimate ancient temperatures. These data clearly show that the climate of this era was exceptionally mild. To precisely date the Cretaceous, scientists use advanced geochronology techniques. The International Union of Geological Sciences, or IUGS, is the organization responsible for defining its subdivisions. The Cretaceous is divided into two major parts, the Lower Cretaceous and the Upper Cretaceous, each comprising several stages. To set the boundaries of these subdivisions, researchers rely on the study of index fossils, specific geological formations, and precise isotopic analyses. For instance, Recent work conducted on the geological formation of St. Audrey's Bay in the United Kingdom enabled the precise dating of the beginning of the Cretaceous with a very low margin of error using the uranium-lead method. This technique relies on the measurement of minerals like zircon, whose crystalline structure traps uranium that slowly decays into lead. By comparing the proportions of uranium and lead, scientists can estimate the age of rocks with great precision. Cross-referenced with other methods, these data establish the major temporal markers of Earth's geological history. Astrochronology is a major advancement for better dating the Cretaceous. This method establishes a connection between astronomical cycles and variations in geological layers. Geologists observe regular changes in the thickness and color of strata in the field, linked to sunlight variations caused by the oscillations of Earth's orbit and axial tilt. A 405,000-year cycle, visible in the carbonate layers of Colorado, serves as a reference to refine the chronology of ancient events. Synchrotron radiation tomography is a modern technique that uses powerful X-rays to analyze the microscopic structures of fossils without destroying them. Applied to fossil feathers, it allows for the 3D reconstruction of their internal structure with exceptional precision, whether they are from dinosaur feathers or primitive birds from the Cretaceous. This method, called synchrotron microtomography, achieves a precision of about a micron, yen 1.25 of an inch, which is a thousandth of a millimeter. Nanosims is a technique that analyzes the chemical composition of fossils by removing atoms layer by layer with an ion beam. By measuring the isotopes present in fossil shells, it allows the estimation of past water temperatures. Brachiopods, marine animals with bivalve shells, record in their growth layers the chemical variations related to temperature. By comparing these data to references, researchers can accurately reconstruct paleotemperatures. Another complementary technique is LiDAR. A laser technology, it maps the Earth's surface in 3D with great accuracy. Used in the upper Cretaceous sedimentary formations, particularly in the Badlands of Alberta, it helps geologists identify and analyze sediment layers remotely. This technology allows precise delimitation of fossiliferous levels and detection of variations in rock composition. Thanks to LiDAR, our understanding of geology and ancient Cretaceous environments is profoundly transformed. The term Cretaceous comes from the Latin creta, meaning chalk, popularized in 1822 by Belgian geologist Domelius de Halloy after observing the white cliffs of Dover. In the 19th century, these formations were exploited, notably for Limoges porcelain. Chalk, a rock formed from the remains of marine microorganisms, is found in various forms across Europe and beyond. It contains fossils of unicellular algae, coccolithophores, which build the coccoliths that form reefs. Agatha Christie evoked these cliffs as a symbol of invincibility, even though they are constantly eroding. The Cretaceous is not limited to famous dinosaurs. Globally, numerous recent excavations, notably in 2024 and 2025, have uncovered a multitude of new species. These discoveries confirm that the Cretaceous was a true hotbed of biodiversity, both on land and in the oceans. Here are some notable examples, illustrating the richness of animals and plants that thrived during this fascinating period. In 2024, a new elasmosaurid named Triskasaurus sandrae was discovered in British Columbia, dating back to approximately 85 million years ago. These long-necked marine reptiles, related to plesiosaurs, measured several meters or about several yards and fed on fish and small prey. Study of its bones has allowed the reconstruction of its anatomy. Triskasaura likely swam with strength, using its long neck to hunt without moving its massive body. The debate remains open regarding its ability to lift its head out of the water. Research continues to better understand its ecology. A new tyrannosaur, Tyrannosaurus macraensis, was discovered in New Mexico, dating back to about 72 million years ago. An older cousin of the famous Tyrannosaurus rex, it was part of the tyrannosaurids present in Asia and North America. A bipedal carnivore, it had a powerful jaw, a long tail, and a head lightened by large openings behind the eyes. Its muscular body made it a formidable predator. This discovery improves our knowledge of the distribution of large carnivores in the western part of North America. During the Cretaceous, pterosaurs, flying reptiles related to dinosaurs, dominated the skies. In Australia, the discovery of Haliskia peterseni, an Hungarian pterosaur 100 million years, or about 62 million years old, revealed a group with long and toothed jaws, adapted for catching fish. Often equipped with large cranial crests, the purpose of which is still debated, these animals testify to a dynamic aerial fauna in the southern hemisphere. These important discoveries have been published in renowned international scientific journals. The plant kingdom reveals treasures like Archaebuda cretaceae, a fossil flower of 125 million years, or about 78 million years old, discovered in China. Rarely preserved, fossil flowers are observed in a few exceptional sites. Archaebuda shows traits of the earliest flowering plants, with separate floral parts and small buds. This discovery illustrates the angiosperm radiation, the rapid rise of flowering plants that transformed Cretaceous ecosystems. Thanks to their adaptations to attract pollinators and disperse seeds, these plants stimulated the evolution of insects and the diversity of herbivores. The Cretaceous also included mammals, small but diverse and well adapted to their environment. In 2025, a major discovery revealed a gelastid in the Gobi Desert, about 90 million years, or about 56 million years old. This group had complex molars, indicating advanced dietary specialization. The fossil, a jaw fragment with teeth, shows dentition adapted for grinding plants or insects. These often nocturnal mammals lived alongside the fearsome dinosaurs and managed to coexist. Their dentition reveals how they gradually developed innovations that would benefit them after the disappearance of the great dinosaurs. Among the terrestrial fauna of the Cretaceous, dwarf sauropods like Petrustitan and Uriash have been discovered in Romania, dating back to about 70 million years, or about 43 million years ago. Their reduced size is indicative of insular dwarfism, a phenomenon where large animals evolve into smaller forms on islands or isolated territories, often due to limited resources. This discovery, arising from international excavations, illustrates how, even at the end of the Cretaceous, dinosaurs occupied diverse ecological niches. The discoveries of 2024 and 2025 show that the study of the Cretaceous is constantly evolving. Paleontologists and geologists are continually pushing our knowledge forward. Each fossil, site, and method of analysis reveals more about ancient fauna, flora, climates, and oceans. They shed light on the evolution of organisms that, in their time, could not imagine the future of Earth millions of years later. In conclusion, the Cretaceous remains a dynamic field of research. Each excavation, method, or interdisciplinary approach reveals the richness of a period that lasted nearly twice as long as the time that separates us from it. Studying the Cretaceous means understanding a major transition in land distribution, climate, and the evolution of life. It also means revisiting a warmer Earth, whose climatic challenges echo those we face today, including rising seas and the management of ecosystems. As we explore this distant past, we will soon prepare to dive into the subdivisions of the Cretaceous, from the Berriasian to the Maastrichtian, each revealing a unique world. For now, let's keep this fascinating overview in mind. Tectonic plates in full swing, vast seas, a warm climate, a dinosaur explosion, the rise of flowering plants, and their consequences for insects. This period precedes one of the most famous mass extinctions, that of non-avian dinosaurs. But at the dawn of the Cretaceous, life still thrives in a vibrant and energetic world that continues to captivate us millions of years later. Let us prepare, because the discoveries to come and the stories of vanished creatures will continue to surprise, question, and amaze us. Here we are at the very beginning of the early Cretaceous, between 145 and 133 million years ago. Two stages succeed each other here, the Berriasian and then the Valanginian. These terms refer to periods marked by distinct tectonic, climatic, and biological evolutions. To situate this, let's remember that the Cretaceous is the last major period of the Mesozoic, often called the Age of Dinosaurs. Although we are far from the gigantic dinosaurs of the late Cretaceous, this era is already fascinating. The continents are fragmenting, the oceans are changing, and life is following new evolutionary paths. We will explore each aspect chronologically: geography, climate, sea chemistry, marine fauna, and then terrestrial fauna and flora. This narrative simply explains each aspect of the Berriasian and Valanginian, without assuming any knowledge. Imagine coniferous forests, swamps, modest dinosaurs, and seas rich in ammonites and marine reptiles, a clear and vivid immersion into a distant world. During the Berriasian and Valanginian, the supercontinent Gondwana, which included Africa, South America, Antarctica, Australia, India, and Madagascar, began to fragment. At the end of the Jurassic and the beginning of the Cretaceous, this block began its gradual dismantling. Its pieces drift slowly, giving birth to the continents as we know them today. Rifting refers to the formation of large faults in a continental region, where the Earth's crust cracks due to divergent forces. Imagine stretching a piece of dough. The surface extends, creating a trough that can become a branch of the ocean if the fracture continues. At the beginning of the Cretaceous, this process began in several areas of Gondwana. The opening of the Falkland and Agulhas basins, off southern Africa and South America, marked the first steps towards the separation of these continents. The South Atlantic Ocean does not yet exist, but great changes are underway. Microcontinents like Lhotse or Elan Bank drift, sometimes captured by the formation of a new ocean or pushed away by the collision of other blocks. The microcontinents drift slowly, carried by plate tectonics, moving a few centimeters or inches per year. Over millions of years, these movements completely change the map of the world. At this time, Pangaea divides into two major blocks: Laurasia in the north and Gondwana in the south. Gondwana gradually fragments, giving rise to today's marine basins. Now let's look towards the western Tethys, a vast region that will become the Mediterranean and its surroundings. Here, neritic carbonate platforms develop in shallow, warm, and bright seas, rich in carbonate deposits from corals, calcareous algae, and plankton. The term neritic refers to these shallow zones on continental shelves. At the end of the Jurassic and the beginning of the Cretaceous, new corals and other reef-building organisms colonize these seas, forming the first large post-Jurassic reef barriers. These sturdy reefs become rich habitats, comparable to today's tropical reefs. In the Berriasian and Valanginian, continents shift, marine basins appear or widen, and marine ecosystems thrive in shallow waters. At the beginning of the Cretaceous, during the Berriasian and Valanginian, the climate was generally warm. To reconstruct these temperatures, specialists analyzed stable isotopes of oxygen present in marine fossils. Isotopes are variants of the same element, differing by their number of neutrons. A key parameter, called delta-18 oxygen, reveals, through the fossil shells of belemnites, cephalopods now extinct, the ocean temperatures of their time. At the beginning of the Cretaceous, the subtropical seas averaged 20 degrees Celsius or 70 degrees Fahrenheit, warmer than during other cold periods. Temperatures varied by region, but the atmosphere remained generally warm, with less difference between high and low latitudes. This situation results from high concentrations of carbon dioxide and the configuration of the continents, which influenced ocean currents differently than today. The carbon cycles tell a fascinating story of the Berriasian and Valanginian. Geochemists study a parameter called delta-13 carbon, which measures the proportion of light and heavy carbon in the Earth's reservoirs. A positive delta-13 carbon, for example, plus 1 per mil, indicates an enrichment in heavy carbon, often linked to an increase in vegetation on the continents. This reduction of carbon dioxide in the atmosphere, called drawdown, is supported by the massive development of Araucariaceae forests, conifers with long spiral needles and large cones that capture more CO2, thus changing the carbon cycles. The carbon cycles of the Berriasian and Valanginian are studied through delta-13 carbon, which measures the proportion of light and heavy carbon. A positive value reflects an enrichment in heavy carbon, often due to increased continental vegetation. This phenomenon is favored by the growth of Araucariaceae forests, conifers with long spiral needles and large cones, which capture more carbon, thus influencing the carbon cycles. At the beginning of the Cretaceous, forests developed in an atmosphere rich in carbon dioxide. The vegetation retains more and more carbon, while the seas remain mild and the Earth, devoid of glaciers, offers a warm climate conducive to life. On the shores and in the shallow seas of the Berriasian and Valanginian, marine life flourishes, particularly with an explosion of diversity among ammonites. This radiation means that several lineages from common ancestors rapidly diversify into different ecological niches. Ammonites, coiled, chambered cephalopod mollusks, were widespread in the Mesozoic. Among them, neoceratid ammonites, distinguished by complex patterns at the internal junction of their chambers, are valuable age markers. Their rapid evolution helps geologists precisely date sedimentary layers. In the Berriasian and Valanginian, inoceramid bivalves make their debut in the seas. These mollusks are distinguished by their massive shells, sometimes similar to oysters, but often much larger, depending on the period. From this early Cretaceous, they form their first colonies, occupying different ocean floors and adapting to various depths and types of substrates. Hybodont sharks, which appeared in the Paleozoic, still swim at the beginning of the Cretaceous. They traverse the Mesozoic before becoming extinct before the Cenozoic era. Their teeth adapted to different diets allow them to dominate shallow seas, hunting on the continental shelf. Their primitive silhouette, compared to modern sharks, remains aerodynamic and effective in open water. Among the most impressive marine reptiles, ichthyosaurs, which appeared in the Triassic, persist despite the decline of some lineages. In 2024, a discovery in Argentina surprised paleontologists. ichthyosaur nests dated to the Valanginian. Until now, it was thought that these reptiles gave birth directly at sea, a practice called viviparity. These nests suggest another behavior, perhaps coastal birthing, where females came to give birth in shallow water or on shores sheltered from predators. This discovery enriches our understanding of their biology and makes us imagine shores animated by these giants protecting their young. In the Berriasian and Valanginian, marine life is dynamic. Ammonites develop, bivalves occupy new niches, hybodont sharks remain dominant, and marine reptiles reveal a complex biology. These evolutions accompany the opening of ocean basins and the formation of shallow habitats. With the fragmentation of continents and the advancement of the sea over plains, new ecosystems appear, and marine fauna continues to adapt and evolve. To complete our view of the Berriasian and Valanginian periods, let's look at terrestrial life. Dinosaurs hadn't yet reached the gigantic sizes of the late Cretaceous, but they were already dominating the large terrestrial vertebrates. Among them, the basal spinosauriforms, carnivores close to ancestral forms, occupied humid habitats. They were often piscivorous, meaning specialized in hunting fish. Ceratoseuchops, discovered on the Isle of Wight, illustrates this group. These dinosaurs frequented river deltas, mixing fresh and salt water, rich in aquatic prey. Like today's crocodiles, they ambushed in shallow waters, equipped with elongated snouts and teeth adapted to catching slippery prey. This unique trait distinguished them from other large theropods, such as allosaurids. The first ornithothoracine birds appear in the sky, especially over coasts and wetlands. This group, more evolved than Archaeopteryx, includes Cretaceous, a primitive bird capable of short flights in wooded environments. Resembling today's insectivorous or omnivorous birds, they glided and flew to escape predators and move between trees. Their existence by the Berriasian Valanginian illustrates the rapid conquest of the skies by feathered dinosaurs, direct ancestors of modern birds. The terrestrial vegetation of the Berriasian and Valanginian periods was dominated by Caryophyllaceae conifers, adapted to the warm and humid climates since the Jurassic. Their dense forests formed vast canopies and produced a lot of biomass. The humid and swampy soils also hosted giant horsetails, close to ferns, reaching several meters or about 10 feet. Their segmented cylindrical stem makes them easily identifiable. At the heart of this lush vegetation, many insects evolved, notably dictyopterans, a group including cockroaches, termites, and mantises. They are distinguished by their tough anterior wings, called tegmina, and their mouth parts adapted to biting and nibbling various materials. A dictyopteran insect trapped in Burmese amber, about 138 million years old, testifies to resin-rich tropical forests in the Valanginian. This resin, mostly produced by conifers, forms amber, a precious material sometimes encapsulating fossilized insects. Burmese amber from Myanmar illustrates the biodiversity of these ancient tropical forests, teeming with life. The warm climate and rising seas created fertile humid plains covered with conifers and giant ferns. These forests provided food for herbivorous dinosaurs and hunting grounds for carnivores. The swampy deltas, frequented by spinosauriforms, abounded in fish. The numerous insects fed the primitive birds and other small animals. A complex food chain was organized, both on land and in the air. Life unfolded everywhere. Each season, terrestrial dinosaurs laid their eggs in nests dug in the ground, while some marine reptiles, like ichthyosaurs, might have come near shores to reproduce. The dense forests sheltered small primitive rodents and insectivorous mammals, though their fossil traces are rare. In the sky, a few bird silhouettes were drawn, while the warm days echoed with the incessant buzzing of insects. By connecting the studied elements, a clear picture of the Berriasian and Valanginian emerges. Between about 145 and 133 million years ago, the fragmentation of Gondwana gradually modified the geography. New shallow seas spread to the edges of the fractured continents, creating favorable habitats for the emergence of rich marine ecosystems and the development of flourishing coral reefs. The isotopes from belemnites show that the subtropical waters of the early Cretaceous were around 22 degrees Celsius or 72 degrees, a sign of relative warmth. A positive delta-13 carbon indicates an active continental biosphere with the expansion of Araucarian forests. These trees with long leaves formed vast stands that stored carbon dioxide, thus reducing its presence in the atmosphere. In Tasmania, an urtinite reveals that natural fires punctuated these landscapes more than 130 million years ago. Marine life is transforming. The neoceratoid ammonites, those emblematic coiled cephalopods of the Mesozoic, are diversifying into numerous species, both in lagoons and on the continental shelf. Inoceramid bivalves are beginning their evolution, which will take them far beyond this initial stage. Hybodont sharks, formidable ancient predators, still dominate several niches in these warm seas. A recent discovery of ichthyosaur nests on the Argentine coasts reveals a more complex reproductive behavior than simply giving birth in the open sea, showcasing their remarkable adaptation to diverse habitats. On land, basal spinosauriforms like ceratoseuchops hunt fish in the deltas. The first ornithothoracine birds, such as Cretaceous, fly to the canopy to escape predators. The landscape is dominated by Chirolepidaceae conifers and giant horsetails, forming swamps. These habitats host a diverse insect fauna, evidenced by a dictyopteran trapped in Burmese amber, proof of active resin production and fossilization in amber from this time. Imagine a landscape at the heart of a peat bog. A large emergent conifer dominates the scene. Under its shadow, tree ferns and horsetails form a dense undergrowth. A few steps away, a brackish watershore reveals the meeting of river and sea. There, a spinosauriform with a long snout watches for a careless fish. A little further, an archaic bird lets out a cry as it clumsily launches from one branch to another. Around the trunks, insects swirl, some falling into the resin that beads from the cuts left by reptiles in search of food. On the coastal plain, a humid tropical wind nourishes the conifers and refreshes the grassy patches. Further away, in the clear waters, ammonites sail, while hybodont sharks patrol on the hunt. Patient, an ichthyosaur heads towards a coastal refuge to give birth in safer waters, away from predators. A thousand details and interactions compose a living tableau of the Berriasian and Valanginian. These pivotal periods show the intertwining of tectonics, climate, and life. The continents drift, the sea advances, and vegetation changes at the rhythm of salinity, temperature, and fires. Marine and terrestrial animals meet at the boundaries of ecosystems. This scene sets the stage for the rest of the Cretaceous, marked by an impressive megafauna, significant warming, and major upheavals in the history of life. To conclude, let us return to some more precise aspects that may satisfy the curiosity of those who wish to understand more deeply the mechanisms at play. Rifting in Gondwana. Gondwana was the large southern continent formed after the separation of Pangaea into two, in the north, Laurasia, and in the south, Gondwana. At the end of the Jurassic and the beginning of the Cretaceous, divergent forces act between Africa, Antarctica, and South America. In these fractured zones, the lithosphere thins, sometimes allowing magma to rise and form oceanic ridges. The Falkland Basin and the Agulhas Basin, located between southern Africa and South America, mark the beginning of the South Atlantic. Small continental blocks, called microcontinents like Lhasa or Eland Bank, detach. At that time, Africa does not yet move clearly away from South America, but the separation begins to initiate. The neritic carbonate platforms of the Western Tethys. The Tethys was a vast ocean, separating Laurasia to the north from Gondwana to the south. Carbonate platforms are shallow seabeds, called neritic zones, where calcium carbonate accumulates thanks to the shells of corals, bivalves, and calcareous algae, as well as chemical precipitations in warm water. These platforms, often covering the continental shelf up to 200 meters or 656 feet in depth, host reef barriers formed by fixed organisms. These reefs modify marine currents and offer refuge to rich biodiversity. Climate changes and the importance of carbon. The Berriasian Valanginian period was bathed in a warm atmosphere. Isotopic analyses on belemnites indicate that the temperature of subtropical waters was around 22 degrees Celsius or 72 degrees Fahrenheit. These measurements remain averages but confirm the absence of polar ice caps. Furthermore, disturbances in the carbon-13 delta indicate significant forest expansion, notably of the Araucariaceae. By absorbing carbon dioxide, these trees altered the isotopic composition of the atmosphere and oceans. Finally, the presence of fires, evidenced in Tasmania, suggests that droughts or other factors like lightning or volcanism regularly caused natural fires. The radiation of neoceratoid ammonites and the establishment of inospermid bivalves. Over millions of years, ammonites developed a wide variety of forms, sizes, and ornaments, such as ribs, tubercles, or more or less open coils. This rapid diversification at the beginning of the Cretaceous saw the emergence of numerous genera that quickly spread. Inoceramid bivalves, recognizable by their robust and varied shells, made their first appearance in the Berriasian Valanginian before later dominating the Cretaceous seas. Hybodont sharks, contemporaries of these mollusks, remained adaptable predators, crushing crustaceans, shells, and capturing small fish. The triumph of modern sharks, such as lamniforms and carcharodontiforms, would come later. Ichthyosaur nests in Argentina, and the notion of coastal parturition. The reproduction of marine reptiles remains a fascinating mystery. Plesiosaurs, for example, were viviparous, as were some lineages of ichthyosaurs. The recent discovery in 2024 of nests attributed to ichthyosaurs raises questions. Did they seek out shallow waters or shores to give birth, or are they merely fossil deposits trapping embryos? Their hydrodynamic bodies and paddle-like limbs suggested an exclusively open sea life. But this discovery suggests a more complex biology, with varied behaviors during the Valanginian. Basal spinosauriforms, ceratoseuchops, and the conquest of wet environments. Spinosauriforms are a group of carnivorous dinosaurs, linked by skull and tooth traits. Their major innovation, an elongated snout with conical teeth, ideal for fishing. Ceratoseuchops, discovered on the Isle of Wight, is a precursor of this group in the Berriasian Valanginian. These dinosaurs frequented deltas rich in fish and sometimes reptiles, suggesting a semi-aquatic life. With their powerful hind legs, they were formidable both on land and in water. Basal means they remain close to ancestral forms, initiating the lineage of more specialized spinosaurids. They illustrate the diversity of niches occupied by theropods beyond the classic terrestrial tyrannosaurs. Ornithothoracian birds like Cretaceous. The earliest birds, like Archaeopteryx, date from the late Jurassic. In the Berriasian Valanginian, more modern ornithothoracians appear, with a developed keel and a shoulder adapted to flapping flight. Although primitive, their wings and heart progress, improving their flying capability. Small in size, they perch to escape predators. The evolution of feathers and flight follows a long continuum, with Archaeopteryx as a step toward these early Cretaceous birds. Chirolepidaceae conifers, giant horsetails, and swamps. In continental landscapes, vegetation structures, habitats, and creates niches for fauna. The Chirolepidaceae, typical Mesozoic conifers, have small overlapping leaves, visible in some well-preserved fossils. Horsetails, members of the Equisitopsida group, have hollow segmented stems and reproduce via spores, like ferns. These giant horsetails grow especially in wet areas, along rivers and in swamps. During the Berriasian and Valanginian, vast, lush swamps, dotted with towering conifers, stretched under a warm and mild climate. These floodplains were ideal for horsetails, promoting the sedimentation of organic matter that could eventually form coal or other carbon-rich rocks. Burmese amber and the Dictyopteran insect aged. Amber is a fossilized resin exuded by certain trees. It flows down the trunks, trapping insects, spiders, and sometimes small plant debris like dust or pollen. Over time, this resin solidifies and fossilizes. Burmese amber is famous for its conservation quality and the richness of its inclusions. The discovery of a Dictyopteran that is 138 million years old, or about 86 miles old, proves that these insects, such as mantises, cockroaches, and termites, already thrived in tropical forests. This sheds light both on their evolution and the stable, humid climate of these ecosystems, as resin production indicates dense and healthy vegetation. The Berriasian and Valanginian represent a key turning point in Earth's history, preparing for major geographical and climatic upheavals. Throughout the Cretaceous, some animal lineages emerging from this period will thrive, while others will disappear. The configuration of continents will evolve, with seas covering vast regions and isolating island ecosystems. At the beginning of the early Cretaceous, the Earth is bustling with activity. Each underwater ridge, nascent bay, emerging forest, and humid breath in a delta draws the future face of the world. Varied creatures struggle to survive and evolve, leaving fossils that modern science gradually uncovers thanks to its field and laboratory tools. This young Cretaceous rivals the Jurassic in its dynamism, and the transformations initiated will announce the great events of the mid and late Cretaceous. This journey through the Berriasian and Valanginian brings us closer to ancient times. Fossils, isotopes, rocks, amber, and footprints form a puzzle that scientists assemble to create an accurate mural. This era reveals the complexity of the Cretaceous, a warm and lush Earth where marine and terrestrial life evolves at the pace of geological upheavals in a setting mixing forests, reefs, deltas, and temperate seas. This narrative helps imagine the drifting of Gondwana, the expansion of shallow seas, the richness of marine and terrestrial life, and the beginnings of the great upheavals of the Cretaceous. Close your eyes and travel back 133 to 126 million years, or about 83 to 78 miles ago. The landscapes, seas, and continents were unrecognizable. Here we are at the beginning of the Middle Early Cretaceous, at the Hauterivian and Barremian geological stages. During these millions of years, Earth experienced major tectonic transformations, intense volcanism, climatic upheavals, and a thriving marine life. In this chapter, we will explore how the planet transformed, how the climate evolved, and how marine fauna thrived. Prepare yourself for a captivating journey into this fascinating era. At this time, tectonics were still shaping the Earth. The continents, once gathered in the supercontinent Pangaea, had fragmented into several blocks. New oceans were then expanding. During the Hauterivian and Barremian, this intense tectonic activity continued, creating major geological formations. One of the most impressive events of this period concerns the Ontong Java Plateau in the Western Pacific. This vast plateau was formed by immense outpourings of basaltic lava, a fluid lava rich in minerals like pyroxene and olivine, which spread over vast underwater surfaces. About 120 million years, or approximately 75 miles ago, the Earth released an enormous amount of magma through cracks under the ocean. Rather than creating a volcanic chain, this lava spread out to form a gigantic underwater plateau, one of the largest known on Earth. This intense submarine volcanic activity had significant geophysical consequences. When enormous amounts of lava accumulate on the ocean floor, the Earth's mantle below changes in temperature and density. This is known as isostasy, a principle where the lithosphere, the Earth's solid crust, sinks or rises in the mantle according to its weight and thickness. Imagine a piece of wood floating on water. If it becomes heavier or thicker, it sinks deeper. On a large scale, this applies to rocky masses. Thus, the weight of the volcanic plateau alters the way the crust floats on the mantle, causing variations in sea level called eustatic changes. Between the Hauterivian and Barremian, the sea level rose by about 40 meters or 131 feet, at least locally, in connection with the formation of the volcanic plateau and isostatic adjustments. This rise, called marine transgression, pushes water onto the land, flooding coasts and continental basins. Geologists find traces of deep marine environments in sediments where the water was previously shallow. The black shales, dark rocks rich in poorly oxidized organic matter, testify to these conditions. In the Western Pacific, their accumulation coincides with basalt eruptions, helping to trace the history of the seas of this era. Intense volcanism releases large quantities of greenhouse gases, notably carbon dioxide, into the atmosphere. Submarine volcanoes emit lava and dissolved gases, which disperse into the water and air, affecting the climate. These effects will be studied in more detail in the section on climate and anoxic events, key to understanding the planetary dynamics of this period. During the mid-lower Cretaceous, several microplates slowly detached from the supercontinent Gondwana, which at that time was composed of Africa, South America, Antarctica, Australia, and India. This splitting promotes the creation of oceanic basins and shallow seas. Geologists use paleomagnetism, the study of rock magnetization, to track their movements. Although this data is complex, it confirms a vast movement of ocean opening and rearrangement of landmasses during this period. During the Hauterivian and Barremian, basaltic eruptions, continental fractures, and rising seas transform Earth. The lithosphere and asthenosphere confront each other on a large scale, redrawing the world. These movements, invisible to fauna and flora, sculpt geography and influence climate and ecosystems for millions of years. The Cretaceous is often described as a warmer era than ours, with much less icy poles, sometimes without stable polar ice caps. This is referred to as a greenhouse world, a globally milder climate, comparable to the effect of a horticultural greenhouse. However, this warming was not constant. It varied over time and space, with sometimes rapid changes over tens to hundreds of thousands of years, a rapid pace on the geological scale. A major climatic episode of the Barremian is the oceanic anoxic event called OAE-1A, Oceanic Anoxic Event 1A. This crisis, also known as the Selly event, denotes a significant oxygen deficit in the oceans, observed in some rock formations. Dated to about 120 million years ago, it coincides with intensified volcanism on the Ontong Java Plateau. Imagine high concentrations of carbon dioxide in the atmosphere due to immense lava flows and other greenhouse gas emissions. This surplus warms the air and the surface of the oceans. In some marine areas, this warming and water stratification prevent proper oxygen circulation. The deep waters become oxygen poor, creating anoxic environments. Moreover, organic matter accumulates and decomposes, consuming even more oxygen and worsening the situation. Thus, vast oceanic basins see the formation of black shale deposits rich in organic matter. An important sign of this anoxic crisis is the change in the carbon isotopic composition, measured in the carbonates and organic matter of sediments. During the Selly event, researchers observe an increase in the delta-13C value of about 6 per thousand. This term refers to the relative proportion between carbon-13 and carbon-12 isotopes compared to a standard reference. This rise indicates a disruption of biogeochemical cycles related to the massive sequestration of carbon in marine sediments and variations in organic productivity at the ocean's surface. Biomarkers are stable organic molecules preserved in rocks that help reconstruct the activity of ancient organisms or past conditions. Among them, isorenirotine indicates the presence of photosynthetic sulfur-reducing bacteria, which live in low oxygen but light-exposed environments. This phenomenon, called photic euxenia, means that the upper layer of water, bathed in light, is rich in sulfur and low in oxygen. This shows that anoxia was not limited to the depths, but could reach light-exposed areas, endangering most marine animals dependent on dissolved oxygen. Modern modeling sheds more light on this episode. In 2025, studies using the computer model Paleo-3 accurately estimated the carbon dioxide release linked to the rapid formation of the Ontong Java Plateau. These simulations, integrating geochemistry, chemical reactions, and climate feedbacks, show that a large portion of this gas dispersed into the ocean and atmosphere, reinforcing the greenhouse effect. This accumulation of CO2, rising marine temperatures, and water stagnation led to global anoxia for about 1 million years. Although short on a geological scale, this crisis profoundly disrupted the era's life and chemical cycles. After the Anoxia Event 1A, the climate remained unstable before ocean circulation was restored and volcanism decreased. Marine life faced high pressures. Some species adapted, while others disappeared locally. This global shock durably altered biodiversity, leaving visible traces in the fossil record. While the Earth experienced tectonic and climatic upheavals, marine life in the Hodorivian and Barremian diversified despite the local impact of anoxic zones. Among the fish studied by paleontologists, pachycormids attract particular attention. This now extinct family included often gigantic species, some of which fed by filtering plankton. These giant pachycormids are comparable in lifestyle to modern whales, but are not related. This similarity results from evolutionary convergence, where similar pressures lead to similar forms and feeding strategies. During the Middle-Lower Cretaceous, pachycormids, already present since the Jurassic, reached record sizes. Since the late 20th century, it has been known that Leedsichthys, one of the most well-known genera, exceeded 15 meters or 49 feet. But drills at the heart of the Ontong Java Plateau, studied in 2024, reveal fossils suggesting Leedsichthys could reach nearly 20 meters or 66 feet, making it one of the largest bony fish known. This discovery shows how some marine lineages took advantage of the explosion of plankton, stimulated by significant nutrient inputs linked to underwater volcanism. Despite the risks of anoxia, stable niches allowed the survival of these large filter feeders. Let's now discuss lamnoid sharks, a group that today includes famous species like the great white shark and the mako shark. In the Hodorivian and Barremian, these sharks began diverging towards what is known as the lamniforms lineage. The term lamnoid refers to sharks with particular fin and gill slit structures. Their diversification, or radiation, is favored by the emergence of new marine niches and the gradual disappearance of some large Jurassic predators. Paleontologists rely on fossil teeth, often isolated, to date these early lamnoids. These teeth, more resistant than the cartilaginous skeleton, are the main fossil traces. It would be incomplete not to mention another major player in the marine ecosystems of the Lower Cretaceous, the rudists. These bivalve mollusks, often mistakenly confused with corals, built large reefs with their conical shells. Simply put, they played a role comparable to that of corals in modern reefs. During the Barremian, rudists developed digitate architectures, forming colonies in the shape of fingers or narrow rows rising upwards. This structure favored light capture and provided habitats for other organisms. Rudist reefs did not only form in perfect waters. While some vast oceanic areas became low in oxygen, others closer to the coasts or on shallow plateaus remained well oxygenated thanks to currents. There, rudists thrived, associating with other organisms to create a rich mosaic of biodiversity. With volcanism altering the ocean's chemistry and the drifting plates, some of these communities were trapped in declining basins or buried under new sediments. Thus, they left in the geological records a trace of a particularly dynamic biosphere from the early Cretaceous. Beyond the giant pachycormids, nascent sharks, and rudist reefs, the marine biodiversity of the early Cretaceous included many other life forms. Ammonites, the emblematic cephalopods of the Mesozoic, inhabited diverse habitats, from the surface to great depths. Sometimes, they served as prey for marine reptiles or sharks. Bivalves and gastropods, like marine snails, diversified in coastal environments and shallow lagoons where conditions were favorable. Some crustaceans, notably primitive crabs, also appear in fossils, although often fragmentary. During the Hodorivian and Barremian, ichthyosaurs and plesiosaurs persisted despite less diversity than in the Jurassic. These marine reptiles adapted to various prey. Ichthyosaurs fast and dolphin-shaped, hunted fish and cephalopods, while plesiosaurs with long necks stalked their prey in reefs or open sea. All these animals underwent, to varying degrees, the effects of global warming and partial marine anoxia. Those capable of migrating to better oxygenated waters or less hostile environments had a better chance of surviving and passing on their genes. The others, less mobile or too specialized, struggled to adapt. Despite an apparently flourishing biodiversity, natural selection was relentless at that time, eliminating any weakness in the face of these rapid changes. The principle is simple: the fittest thrive, while the weakest disappear. The marine fauna of the Hauderivian and Barremian reveals an impressive richness and resilience, despite the climatic and geochemical upheavals of the time. The pachycormids, gigantic filter-feeding fish, rival in size with some giants of other periods. Lamnoid sharks gained importance, heralding a lineage still present today. Rudists, reef-building mollusks, innovated with complex architectures, creating varied habitats where numerous marine animals thrived. Despite episodes of anoxia, high volcanic activity, and sea level fluctuations, marine life continued to explore and occupy every oxygenated niche. During the early Cretaceous middle, tectonics shaped a vast oceanic plateau that amplified volcanism and modified the Earth's crust. The warm climate, strengthened by greenhouse gases, was accompanied by an oxygen deficit at depth. These dynamics transformed seas and continents over millions of years. In the face of these upheavals, marine life adapted and developed new strategies, preparing for the major transformations of the late Cretaceous. Today, modern science derives immense knowledge from studying these ancient events. Researchers explore fossil records, sediment cores, chemical compositions of rocks, and microfossils to reconstruct the Earth of the past. In our studied period, the combination of varied clues paints a clear picture of marine life and environment of the early Cretaceous middle. Despite the millions of years that separate us, each new research refines this portrait, revealing the complexity of the mechanisms at work. To conclude, let's remember that the Ontong Java volcanic plateau, isostatic adjustments, and the rise in sea level, along with the oceanic anoxic event 1A, profoundly shaped the seas of the Hauderivian and Barremian. Despite the constraints of anoxia, localized or temporary episodes offered refuges for life, allowing the emergence of evolutionary innovations. In these oceans, filter-feeding giants like Leedsichthys coexisted with the ancestors of modern sharks, while rudist reefs erected new biological barriers. Every oxygenated water became a haven where life continued its epic journey. Let's dive into the late Lower Cretaceous, a period often overlooked but rich in upheavals and new forms of life, spanning from 126 to 120 million years ago. This period, divided into two stages, the Aptian and the Albian, marks deep transformations on Earth. Although the planet was already several billion years old, it was still undergoing significant changes. The continents were drifting, oceans were changing size, and marine and terrestrial groups were experiencing peaks of diversity or disappearing. We will explore the key phenomena of geodynamics, climate, marine anoxia episodes, and biological radiations that marked these millions of years. Although this period is brief in Earth's history, it is essential for understanding the current configuration of continents and today's biodiversity. We will take a simple chronological approach. First, geodynamics and its effects on oceans and sedimentary basins. Then, we will study the adaptive greenhouse climate, followed by the OAE-1b anoxic event and its consequences. Finally, we will explore biological radiations, with dinosaurs like spinosaurids, titanosaurs, and crested pterosaurs, as well as a major fossil flower. Everything will be explained clearly to make this chapter of the Cretaceous accessible. Towards the end of the Lower Cretaceous, the separation of Africa and South America marks a major turning point. The continents, once connected, separate under the influence of internal forces of the Earth. These forces, generated by the heat of the Earth's mantle, cause tectonic plates to drift and create new zones of divergence, thus forming oceanic lithosphere. To understand how the separation of Africa and South America accelerated, imagine a scar under the ocean, the Mid-Atlantic Ridge, an underwater mountain range formed by solidification of magma rising to the surface. In the Aptian and Albian, the expansion rate of this ridge increased, extending the ocean surface more rapidly. It's like a seam that comes undone quickly, with two sides moving apart. The immediate result is the widening of the Atlantic Ocean between Africa and South America. The opening of the ridges leads to a global rise in sea level. When production of new oceanic crust is intense, the ridge takes up more volume and pushes water towards the continents. A warm climate also reduces ice formation at the poles, thus increasing sea levels. Paleontologists and sedimentologists identify these rises through marine deposits on formerly emergent areas, or through geological strata showing the transgression of the sea onto the lands. Some regions of Africa and South America retain traces of this marine advance on lands now well inland. In Brazil, during the late Lower Cretaceous, Aptian lacustrine basins accumulated organic sediments in oxygen-poor environments, creating source rocks for hydrocarbons. These rocks release oil under pressure and heat, and the pre-salt layer contains significant reserves. The term pre-salt refers to a time before the deposit of salt in the South Atlantic. The separation of the South American and African plates generates new marine spaces and influences the distribution of mountains, sedimentary basins, and ecosystems. Continental drift, though slow on the human scale, alters Earth's geography over millions of years. At a speed similar to that of nail growth, these movements gradually redefine the planet's contours. Evidence of this transformation includes rock outcrops that were once marine, now continental, as well as the morphology of coasts, revealing the history of these geological separations. The climate of the Aptian and Albian, known as adaptive greenhouse, was very warm, with carbon dioxide levels reaching 1,000 parts per million, much higher than current levels. This high concentration is explained by more active volcanism, dynamic tectonics, and the expansion of the oceanic crust, which released large quantities of gas. Other processes, like the decomposition of organic matter, also contributed to this warming, although to a lesser extent. Paleontologists and paleoceanographers reconstruct the temperature of ancient waters by studying the oxygen isotopes found in fossilized shells and marine bones. By comparing the proportions of light and heavy oxygen, they determine the water temperature and salinity where these animals lived. In the Aptian-Albian period, fossilized ichthyosaur teeth reveal that water temperatures up to 60 degrees north latitude reached about 25 Celsius or 77 degrees. This shows that tropical conditions extended almost to the polar circles, reducing the temperature gradients between the equator and the poles. The warm climate favors strong evaporation of seawater, thus increasing atmospheric humidity and enhancing the greenhouse effect. Rather than imagining a tranquil world, it seems these conditions caused major disturbances. including more intense storms and cyclones. According to a climate model published in 2024 by the University of Cambridge, a belt of cyclones would have crossed the subtropical and tropical regions, with possibly higher intensity and frequency than today. The Aptian Albion was therefore not a calm world, but rather a dynamic environment where violent cyclones could cause heavy rainfall and accelerate coastal erosion. The warm climate influenced the distribution of forests, dominated by primitive conifers and seed plants. The ecosystems resembled vast, dense, lush subtropical landscapes. The coasts, subject to floods and marine storms, gave rise to swamps and mangroves where many species of insects and amphibian reptiles developed. Oceanic anoxic event 1b, which occurred during the Aptian and Albion, marks a drastic drop in oxygen levels in the oceans. This lack of oxygen disrupts the decomposition of organic matter, like plankton and algae, which accumulate in sediments. This process leads to the formation of dark rocks called black shales, resulting from the accumulation of poorly decomposed organic matter. Oceanic anoxic event 1b, occurring in the late Lower Cretaceous, is well documented in Folkestone, England, where Albion black shales are found. These dark sediments show an oxygen-depleted sea, preventing marine fauna from surviving. This phenomenon results from several factors: a changed climate, increased water stratification, and an excess of nutrients from the continents. When these nutrients reach the sunlit zone, algae proliferate, and their decomposition consumes oxygen in the deeper waters. To understand this anoxic event, scientists analyze neodymium isotopes. These variations reveal oceanic water sources and circulation changes over time. In the Aptian Albion, upwelling, or the rise of deep waters, would have disrupted the chemical balance of the water column. Rich in nutrients, these waters favored a proliferation of phytoplankton, leading to a biomass peak, followed by oxygen depletion in the lower layers during organic degradation. Imagine vast marine stretches where enormous productivity clashes with the asphyxiation caused by the decomposition of this abundance. The impact on biodiversity is reflected in the fossil records. It is estimated that about 30% of planktonic foraminifers of the Hedbergelidae family experienced rapid extinction. These organisms, with calcareous shells, are used to reconstruct the state of the oceans and the health of the marine ecosystem. Variations in their diversity reveal the state of the ocean surface, influenced by changes in ocean chemistry, such as a drop in pH or lack of oxygen. While larger fauna, such as fish and some invertebrates, escaped massive extinction, they still locally declined depending on the anoxia. Oceanic anoxic event 1b remains a key research subject to understand Earth's reaction to warming and high marine productivity. At the end of the Aptian and Albion, despite ecological imbalances, significant biotic radiations occurred with the rapid diversification of new species. Biotic radiations refer to the proliferation of groups that colonize new niches. Among the most notable groups of this period are Spinosaurids, certain Titanosaurs, several lineages of pterosaurs, and rarely, ancient fossil flowers. Spinosaurids, piscivorous predators, diversified during the Aptian-Albion period, notably with Suchomimus, discovered in Niger. Its name, crocodile mimic, refers to its elongated skull. Unlike some later spinosaurs, its vertebrae do not form a dorsal sail. Adapted to a piscivorous diet, Suchomimus likely lived in deltaic regions where it hunted fish. This diversification of Spinosaurids suggests ecosystems rich in aquatic prey, probably favored by a warm climate and the presence of seas in some inland basins. In the domain of herbivorous dinosaurs, the titanosaurs are distinguished by their impressive size, long necks, and tails. In the Aptian of Brazil, a basal titanosaur was found, plesiosaurs. This herbivore, with a skull featuring a shortened snout, differs from other titanosaurs with more elongated jaws. Plesiosaurs represents a key stage in the evolution of sauropods, with both primitive and advanced characteristics. The vast floodplains and humid forests of Brazil at the time likely fostered the growth of these large herbivores, nourished by dense vegetation and benefiting from a mild climate. Pterosaurs dominated the sky of the late Lower Cretaceous, with varied and specialized forms. Among them, Hungarians are notable for their conical-toothed jaws and bony crests. In Australia, fossils of Halischia peterseni, dating from 100 million years ago, reveal sagittal crests. Their function is debated: courtship display, thermal regulation, territorial signal, or ornament. This morphological diversity shows the dispersal of pterosaurs across continents, still closely connected at the time, thanks to relatively narrow land or marine corridors. One of the notable discoveries in Cretaceous paleobotany is the fossil flower Archaebuda cretaceae, found in China and dated to 125 million years ago. It confirms the presence of angiosperms as early as the Aptian Albion, much earlier than previously thought. Its floral buds, 4 millimeters or 0.16 inches, show primitive anatomy, with simple, unfused carpels, illustrating an experimental stage in floral reproduction. Paleobotanists believe these flowers thrived in humid environments, favored by warmth and abundant rainfall. The appearance of angiosperms like Archaebuda cretaceae marks a turning point in terrestrial ecosystems, disrupting the dominance of conifers, cycads, and ferns. Flowering plants introduced crucial innovations, such as insect pollinators and fruits with protected seeds. Although modest, Archaebuda cretaceae is part of this transformation, offering botanists a key to understanding the evolution of more complex floral forms and the diversification of pollinating fauna. These early flowers were likely visited by primitive insects like flies and beetles. The Aptian Albion is not limited to a simple geological transition, but represents a period of intense evolutionary dynamics. Although extinctions and episodes of anoxia mark upheaval, they do not signify the end of life, but rather an ecological renewal where certain lineages adapt and thrive. Piscivorous dinosaurs, like spinosaurids, exploit marine and riverine resources in a warm climate. Titanosaurs, increasingly gigantic, specialize in grazing adapted vegetation. Pterosaurs, on the other hand, multiply in forms and occupy skies marked by storms. On land, flowering plants, still modest, initiate a revolution that will profoundly transform the plant kingdom. It is fascinating to see how geological and biological trajectories intertwine. The gradual separation of Africa and South America alters ocean currents, influencing the climate, which in turn affects phytoplankton productivity, contributing to anoxic episodes. Meanwhile, Brazilian lacustrine basins become evolutionary hotspots for certain vertebrate lineages due to their uniqueness. The warm climate favors a proliferation of life forms, generating a diversity of ecosystems. Paleontologists' work is to piece together this puzzle, whether it's a fragment of dinosaur jaw, a fossilized tooth, or a floral bud. Each discovery adds a new page to the story of this fascinating epoch. The late early Cretaceous is a time of geological, climatic, and biological changes. Through the dynamics of continents, the evolution of marine ecosystems, and the emergence of new species of dinosaurs, this period illustrates the ability of species to adapt or disappear in response to the evolution of their environment. This complex interplay between geological and biological forces foreshadows the late Cretaceous, where animal lineages already present will thrive until the major extinction at the end of this era. For contemporary research, the Aptian and Albian represent a crucial window for understanding the links between tectonics, climate, ocean chemistry, and biodiversity. Studying this period helps to address questions about ocean circulation or the effects of greenhouse gases. With modern tools like microscopic observation, isotopic analysis, and climate modeling, researchers faithfully reconstruct this lost world. The stakes are multiple: understanding Earth's place in its history, the resilience of life in the face of environmental disturbances, and the complexity of interactions between the mineral, living, and atmospheric. Over the years, the rediscovery of major fossil sites from this period in Africa and South America has advanced thanks to the search for oil deposits and the exploitation of geological sections. Paleontologists have found direct evidence, such as Piscine dinosaur bones with fish tooth marks, indicating their dietary specialization. Other fossils reveal the presence of a vast network of lakes, swamps, and estuaries. In Brazil, some anaerobic zones have preserved plant organic matter and fish remains. Geologists analyze the marine and lake sediments of the time to reconstruct the geodynamic history of the region and the early stages of the South Atlantic. We note the convergence between paleontological and paleobotanical studies. The discovery of the fossil flower Archaebuda cretaceae in China, associated with other small floral structures in Asia and on ancient fragmented continents, reveals the diversity of terrestrial ecosystems, ranging from marshy shores to moist forests of modest altitude. These flowering plants, which appeared at the beginning of the Aptian, coexisted with a varied dinosaur fauna and probably benefited from pollination by insects such as beetles and flies. Among marine radiations, there is the rise of bony fish, moving in schools in nutrient-rich coastal waters. Coral reefs, dominated by rudist bivalves, vary by region. In some areas, warm water and low oxygen slow their development, while in others, nutrient input promotes the growth of reef communities. Pterosaurs, gliding above, serve as prey for larger predators, illustrating the interconnectedness of species in these complex ecosystems. At this stage, the climate remains generally warm and little affected by major glaciations. Some signs of relative coolness occasionally appear in altitude formations, notably through certain variations in the marine planktonic fauna or isotopic readings, but these signals remain marginal. The Earth functions then as a vast greenhouse, where heat is trapped by carbon dioxide and other greenhouse gases. This atmospheric envelope acts as a thermal insulator. The drift of continents and the expansion of ridges release volcanic gases, gradually enriching the atmosphere with carbon dioxide. How does this panorama shed light on the dynamics of terrestrial and marine life? Organisms capable of strong physiological adaptation or exploring new niches thrive. Conversely, constrained ecosystems, especially those near zones of repeated anoxia, suffer a drop in diversity, as evidenced by certain planktonic foraminifera, with losses of up to 30%. These anoxic events are powerful ecological stressors. Yet, above the seas, other lineages like pterosaurs and large long-necked dinosaurs thrive, benefiting from the warmth and vast vegetated landscapes. On a global scale, this dynamic influences the future structuring of biodiversity. For example, spinosaurids, adapted to fish hunting, represent a key milestone in the diversification of theropod dinosaurs. Some would later develop even more extreme traits, but as early as the Aptian Albion, a phase of morphological innovation already allowed them to expand widely. The same logic applies to giant herbivores. The lineage of titanosaurs is strengthened, and Plesiosaurus sheds light on an essential evolutionary link, showing how these sometimes perplexingly shaped colossi spread across several continents. Biological radiation is fully manifested in the fossils found in the Albian strata, where vertebrate diversity continues to increase, except in anoxic environments. Land corridors favor dinosaur dispersion, while the configuration of the seas initiates differentiation of marine fauna. The advent of angiosperms, though measured at first, gains momentum, and flowering plants like Archaebuda cretaceae settle in warm, wet habitats, offering new resources to fauna. The Aptian Albion beautifully illustrates how Earth combines upheavals and innovations. These millions of years bear witness to nature's resilience. Facing environmental transitions, some species disappear while others multiply, occupying new spaces. It's essential not to confuse human timescales with geological ones. These mutations, although perceived as gradual today, seem sudden when compressed into sedimentary strata. In sum, the late Lower Cretaceous history, from the Aptian to the Albion, illustrates the interconnection between Earth's dynamics and life. Plate drift and the opening of ridges raise sea levels, altering the climate and the distribution of habitats. Carbon dioxide amplifies the greenhouse effect, triggers cyclones, and creates anoxic events. But at the same time, the diversification of dinosaurs, pterosaurs, and the emergence of primitive flowers testify to evolutionary resilience in the face of geological upheavals. The millions of years of the Aptian Albion, rich in fossils and geological formations, continue to fuel fascinating discoveries. Thanks to recent excavations and techniques like X-ray microtomography and mass spectrometry, new questions arise. How did dinosaurs distribute themselves between Africa and South America during the drift? What impact did the additional hundreds of parts per million of carbon dioxide have on marine fauna? What did the landscapes look like where Archaebuda cretaceae blossomed? These mysteries stimulate scientific research and shed light on the complexity of this era. Thus ends our journey into the Aptian Albion. The early Upper Cretaceous, spanning from 100.5 to 89.8 million years before our era, is a key period in Earth's history. The oceans are larger, the continents fragmented, and the climate very mild, allowing vegetation and fauna to expand widely across the planet. It's a time of great geological and biological transformation, with profound changes in ecosystems. Now, we will explore the Sino-Turonian period, which includes the Cenomanian and the Turonian, by analyzing the geological, climatic, and biotic evolutions characteristic of these millions of years. We will first describe the organization of continents and seas, then address the climatic conditions of the time, followed by a major oceanic upheaval known as the Oceanic Anoxic Event number 2. Next, we will discuss the evolution of marine fauna, marked by the emergence of powerful predators and significant species diversification. Finally, we will highlight terrestrial life, where dinosaurs and other groups evolve with impressive dynamism. The Sino-Turonian is a key period for understanding the paleogeographic history of the continents and their coasts. It is during this time that one of the largest inland seas was established, connecting the Gulf of Mexico to northern polar waters. Sometimes called the Western Interior Seaway, this sea covered a large part of North America, separating the lands to the west and east. This configuration had significant consequences on the distribution of marine and terrestrial faunas on the North American continent at the time. The climate of the Cenomanian-Turonian is extremely hot and humid, often described as a super greenhouse due to high concentrations of carbon dioxide in the atmosphere. In some areas, tropical water temperatures can reach 30 degrees Celsius or 86 degrees Fahrenheit, several degrees higher than current tropical averages. This warming directly influences ocean current circulation, biological productivity, and the composition of sedimentary deposits. A major global marine anoxia event occurs, leading to the formation of organic-rich sediments called black shales. This phenomenon, indicative of severe oxygen deficiencies, is well documented, notably in Italy, where the Bonarelli layer contains traces of massive mortality among marine animals unable to adapt to this condition. Now, let's dive into the details of this fascinating period, organized into several parts. The tectonic dynamics of the Cenomanian and Turonian lead to significant changes in the arrangement of the continents and oceans. The drift of the continents, already underway, accelerates, particularly with the rapid expansion of the Atlantic Ocean. The very active mid-Atlantic ridge generates a large amount of oceanic lithosphere. This tectonic activity contributes to a global rise in sea level, altering the geography of the Earth at the time. The term eustasy describes global sea level variations. During the Cenomanian, a major marine transgression occurs, with the sea covering vast lands that were once emerged. In North America, the Western Interior Seaway stands out. This immense body of water, reaching up to 1,000 kilometers or 621 miles wide, connects the Gulf of Mexico to northern Canada, even extending towards the Arctic Ocean. Some areas of this sea, deep and poorly lit, host life forms specialized in extreme ecological niches. The Western Interior Seaway profoundly changes the distribution of fauna and flora. Dinosaurs concentrate on coastal areas, while the continent's interior becomes a vast aquatic environment. Sediments bear witness to this shift. The geological layers reveal alternations of limestones, marls, and sediments rich in microfossils. Coccolithophores, plankton that produce microscopic calcium carbonate plates, proliferate in these warm waters, contributing to the formation of chalks, such as those of the White Cliffs of Dover in the United Kingdom. These fossils provide a detailed view of the climatic and oceanic history of the Cretaceous. Active tectonics, by swelling ocean ridges, reduces the volume of deep basins, leading to a global rise in sea levels. At the same time, the warm climate favors the thermal expansion of seawater, also contributing to this rise in sea levels. This phenomenon is manifested in geological deposits, with the appearance of large marine basins, reef barriers, and thick limestone sediments, evidencing the intensification of these processes. In France, Germany, and Western Russia, fossils bear witness to this marine transgression, with the frequent presence of ammonites, marine mollusks with spiral shells. Their great diversity in the Cenomanian reflects high marine vitality. Bivalves, notably rudists, also abound in these shallow environments, sometimes forming true reefs. Their fossils are widely found in the Cretaceous limestone layers around the Mediterranean basin. The Cenomanian-Turonian paleogeographic tableau reveals a world fragmented into continental blocks, surrounded by vast epicontinental seas. Eustatic variations signal a period of high sea level, with chalk deposits rich in diverse organisms and microfossils. The marine environment predominates, favoring exchanges between basins, species dispersion, and the creation of new ecological niches. This dynamic marine framework stimulates the evolution and biological diversity of this period. During the Cenomanian and Turonian, the climatic conditions are described as super greenhouse, a state where global temperatures are particularly high and the polar ice caps are absent. The polar zones are devoid of ice, favoring the flourishing of forests and fauna adapted to the extremes of summer and winter. In the tropics, sea temperatures reach 30° or 86°, much higher than those observed today. The Cenomanian-Turonian warming is due to a high concentration of greenhouse gases, especially carbon dioxide, estimated at around 2,030 parts per million, which is much higher than current pre-industrial levels, about 280 parts per million. This concentration, combined with increased activity of mid-ocean ridges emitting volcanic gases, results in a reinforced greenhouse effect, trapping solar radiation and causing notable terrestrial and marine warming. Climate warming amplifies the water cycle, increasing evaporation and the air's capacity to hold moisture, which promotes abundant rainfall. This nourishes vegetation and aids in the burial of carbon in the form of organic matter. At the same time, extreme weather phenomena, such as more powerful hurricanes, occur over very warm tropical seas. Atmospheric modeling studies show that these cyclones would be more frequent, more intense, and deposit heavy rains, quickly reshaping coasts and deltas. This mild climate favors biodiversity, particularly in temperate and subtropical regions, where geographic barriers are reduced by marine transgression. Coastal areas are dominated by humid forests of conifers and primitive seed plants, while tree ferns thrive in swamps and along riverbanks. The flora also evolves with the continental drift to higher latitudes, benefiting from global warming. Sediments reveal pollen and spores of plant species, illustrating a complex ecosystem and high primary productivity. Meanwhile, the warm ocean stimulates the expansion of coral reefs, composed not only of modern corals, but also rudists and other reef-building organisms. In shallow and clear waters, light stimulates photosynthesis, thereby increasing the local oxygen rate and trapping carbon in the sediments. However, this favorable climate presents risks. Warmer waters hold less oxygen and slow ocean circulation, which can lead to anoxic crises, like those related to the oceanic anoxic event number 2. Evidence of the extreme heat of this period is based on the analysis of oxygen isotopes found in marine fossils. Organisms such as foraminifera or bivalves, which form shells or skeletons, incorporate minerals whose isotopic composition varies with water temperature. Paleoclimatologists use this information to estimate the temperatures of the time. The results reveal temperatures much higher than today, confirming that the Ceno-Turonian marks a major peak in global warming, a super greenhouse with notable ecological consequences. The Ceno-Turonian climate is characterized by high oceanic and atmospheric temperatures, local variations in precipitation, and an almost complete absence of ice at the poles. These conditions favored an impressive diversification of marine and terrestrial life. However, this balance remains fragile, as evidenced by the planetary anoxic episode, which highlights the climate system's ability to tip toward extremes. This complex dynamic is essential to the paleontological and geological understanding of this era. The Oceanic Anoxic Event number 2, OAE2, marks a major episode of oxygen deficiency in the oceans at the Cenomanian-Turonian boundary, often called the CT boundary. Anoxia refers to an almost total lack of dissolved oxygen in the water, causing mass extinctions, as many marine organisms depend on oxygen. When this depletion prevents the degradation of organic matter, it accumulates in the form of carbon-rich sediments, which, under pressure and temperature, transform into black shales. During OAE2, a positive carbon excursion occurs, marked by an increase in the heavy carbon-13 isotope in geological records of around +5 per mil. This phenomenon is found in both carbonates and fossil organic matter. It suggests a massive trapping of carbon in sediments and significant changes in the global carbon cycle. Increased biological productivity at the surface leads to the accumulation of organic matter, the decomposition of which consumes oxygen. If ocean circulation is insufficient, this leads to anoxia in deep waters. The anoxia of the OAE2 severely affects marine fauna, particularly ammonites, which lose up to 40% of their species in certain regions. Other groups like mollusks and planktonic foraminifera also suffer significant losses. However, well-ventilated marine areas with strong currents or oxygen input from the atmosphere maintain relatively rich life. In contrast, basins where the water is stratified become critical, as evidenced by the Bonarelli black shales in Italy. They illustrate the exceptional accumulation of organic matter in persistently anoxic conditions. Recent studies on biomarkers, such as glycerol dibiphenyl glycerol tea tree ethers, indicate the presence of methanogenic archaea, methane-producing microorganisms in sedimentary layers. Their abundance suggests that extreme anoxic conditions prevailed, allowing these archaea to thrive. These organisms normally live in environments without oxygen, such as marshes or hot springs. Their presence in marine sediments indicates a notable expansion of anoxic zones and increased methane production. This could have intensified the greenhouse effect, as methane is a much more powerful greenhouse gas than carbon dioxide in the short term. The decrease in oxygen in deep waters sometimes accompanies surface disturbances, notably a slowdown in nitrification. In other words, the conversion of ammonium into nitrate by specialized bacteria is hindered. This disruption limits available nutrients, disrupts the marine food chain, and can lead to extinctions or species readjustment. According to some researchers, the origin of the OAE2 is multifactorial. On one hand, intense volcanic activity related to the formation of vast oceanic plateaus or igneous provinces releases significant amounts of carbon dioxide and other gases. On the other hand, the already warm climate reduces the solubility of oxygen in the oceans. Added to this is a massive influx of nutrients from the continents, carried by rivers during a period of high sea levels. These nutrients fuel planktonic blooms, whose decomposition consumes dissolved oxygen. The result, widespread marine anoxia, a typical marker of OAE2. This phenomenon illustrates the ocean system's vulnerability to extreme greenhouse conditions. It shows how global warming, combined with intense geological activity, can disrupt ocean chemistry and cause major environmental crises. Despite the disturbances experienced by marine life, the biosphere gradually adapts, developing new survival strategies. This does not erase the immediate severity of the event. OAE2 thus represents a major ecological catastrophe in many marine basins. Parallel to the impact of anoxia, and sometimes even amidst the crisis, Cenomanian-Turonian marine life experiences marked diversification in some groups, while others decline. Among the newcomers, mosasaurs emerge in force. These marine reptiles, close relatives of today's lizards, gradually replace former great predators. Some reach more than 10 meters or 33 feet. Their elongated bodies, equipped with flippers instead of limbs and a powerful tail, make them formidable hunters, capable of capturing fish and large marine vertebrates. In the United States, in the Kansas region, Paleontologists discovered in 2024 an intriguing fossil shark, Cretaceous hautinorum. Its teeth, found within prey remains, demonstrate its ability to capture large prey. The fossils suggest a varied diet, ranging from small fish to larger prey. There's also the emergence of primitive swordfish like Zephyr with elongated rostra, already adapted to cut through water and potentially strike or disorient prey, foreshadowing modern swordfish. In warm and well-lit waters, schools of ichthyosaurs, once very prosperous in the Mesozoic, persist despite their decline and reduced diversity. Other groups, like plesiosaurs, particularly elasmosaurs, remain present. In 2024, the discovery of Trascosaurus sandrae, an elasmosaurid dated to about 85 million years ago, was presented as a precursor close to the end of the Cretaceous. This finding reinforces the idea that these reptiles, with sometimes very long necks, slow swimmers, and ambush predators, remained active in the interior seas and the large ocean basins. During this period, traditional corals coexist with rudists, bivalve mollusks, capable of forming imposing reefs. One of their valves, often conical, anchors to the bottom, while the other serves as a lid. True marine architects, they create barriers housing fish, crustaceans, and numerous invertebrates. Some reefs develop in warm lagoons with high salinity, forcing species to adapt to sometimes extreme conditions. The planktonic community also undergoes profound changes. Planktonic foraminifera, the first links in the marine food chain, lose certain genera during OAE2, while others specialize or colonize vacant niches. The coccolithophores, producers of calcareous chalks, remain abundant, especially in shallow, well-lit seas. As for diatoms, microscopic algae with siliceous walls, they begin a moderate expansion before their major rise in the Cenozoic. In the deep marine depths, where light does not reach and oxygen is scarce, the fauna adapts to a depleted environment, taking advantage of organic debris falling from the surface. However, the extreme anoxia caused by OAE2 can locally sterilize the seabed, leaving only specialized bacteria or archaea capable of surviving these extreme conditions. The Cenomanian-Turonian marine fauna reflects a fascinating paradox: a spectacular diversification in some marine reptiles, fish, and reef mollusks, in contrast to crises affecting species sensitive to the lack of oxygen. It is a time of ecological innovation, where evolutionary balances are overturned by climatic, marine, and chemical variations. As the marine environment is deeply transformed during the Cenomanian-Turonian, terrestrial life also evolves. The advance of inland seas reshapes habitats. Coastal plains expand, creating vast wetlands favorable to aquatic plants and marsh-dwelling animals. Higher up, flowering plant forests thrive, while ancient conifers, similar to araucarias, persist in remote areas. These environments offer refuge and food to many dinosaur lineages. Among herbivorous dinosaurs, primitive hadrosaurs experience significant growth. Called duck-billed dinosaurs, they possess a broadened snout with rows of teeth adapted to tough vegetation. Probably gregarious, they migrate according to seasons and resources. Their expansion, favored by river systems fed by a super greenhouse climate, allows them to exploit a wide variety of vegetation. This group will play a major role until the end of the Cretaceous. At the same time, the first protoceratopsid-type ceratopsians appear, notably in Central Asia. These quadrupedal herbivores, with a bony frill at the back of the skull, and a horned beak at the front, announced the famous Triceratops lineage. Although modest in size during the Cenomanian-Turonian, they already possess a typical morphology, with a massive head and distinctive cranial armor. Their fossils are found in coastal plains, where they grazed on low vegetation fed by a warm climate. The presence of carnivorous dinosaurs is also evident. Some medium-sized theropods are well adapted to hunting in more or less humid environments, while others, much larger, roam the forests and marsh edges. Coexisting in these shared territories sometimes involves fierce food competition, to which only the most versatile or highly specialized species can withstand. Terrestrial ecosystems thus evolve in a mosaic pattern, with, on one side, vast littoral or marshy areas where vegetation is abundant, and on the other, denser forested massifs, where the fauna is likely more discrete and specialized. The diversity of insects at this time is remarkable. The Myanmar amber deposits from the Cretaceous have yielded in 2024 an aquatic beetle from the Cenomanian, described as a diver beetle. Preserved with fine details, segmented swimming legs, hydrodynamic abdomen, and possible pigments, it demonstrates an advanced adaptation to freshwater life. This discovery reveals that these environments were already well colonized by beetles, while dinosaurs dominated the land and marine reptiles ruled the oceans. It illustrates the complexity of the Cenomanian-Turonian ecosystems, where each habitat, from aquatic depths to the canopy, harbors rich and specialized biodiversity. Mammals remain in the shadow of giant dinosaurs, yet they are far from insignificant. Despite their small size, they diversify into omnivores or insectivores, capable of occupying niches inaccessible to dinosaurs. Some are nocturnal, others are climbers. Their fossils, often reduced to a few teeth or bone fragments, make their study difficult. However, they are already experimenting with different forms of skeletons, dentition, and diet, heralding the rise of the Cenozoic after the extinction of non-avian dinosaurs. At the beginning of the late Cretaceous, the environment is undergoing significant transformation. The Cenomanian and Turonian periods reveal a world dominated by vast interior seas and a super greenhouse climate. Geological records, both marine and continental, depict a changing mosaic of high biodiversity areas and regions marked by anoxia. Marine reptiles like mosasaurs, primitive sharks such as Cretaceous hotenorum, original swordfish, herbivorous and carnivorous dinosaurs compose a tableau of astonishing diversity. The constant adjustment between geology, climate, and evolution can be read in every chalk layer, every black shale, every fossil extracted from sediments. Beyond its particularities, this period illustrates how Earth undergoes strong environmental fluctuations, where temperature, carbon dioxide, and tectonics interact to shape life. The Cenomanian-Turonian represents a key stage, a time of evolutionary explosion, but also of great ecological vulnerability. Across sunlit plains, tropical lagoons, and endless interior seas, this journey has shown us how the study of the Cenomanian-Turonian sheds light on the great mechanisms of Earth, interactions between tectonics and climate, the resilience of the biosphere in the face of crises, remarkable diversity despite challenges, all essential themes revealed by this era. Far in the past, it continues to fascinate scientists and the curious, reminding us that the history of the world is made of sudden and often unexpected upheavals. The study of the early, late Cretaceous offers a glimpse of a planet with a strange configuration to our modern eyes. Yet, one can already discern dynamics and survival strategies foreshadowing future evolutions. By understanding the causes and effects of past warming, anoxia, and diversification, humanity gains valuable keys to facing current climate disruptions. We are now plunged into a new interval of the late Cretaceous, the Coniacian and Santonian, two stages between 89.8 and 83.6 million years ago. This pivotal period is marked by continental movements, sea level variations, and a richness of both terrestrial and oceanic life. For you, curious listeners, we will explore this era step by step, following a clear chronological thread. We will first explore the geological dynamics, then the climatic fluctuations and their effects on marine cycles, before addressing terrestrial fauna and then marine life. We will explain each concept, from island arc collisions to vanished ancient oceans, including armored or feathered dinosaurs and marine giants gliding under the waves. Together, let's embark on this journey into the past, discovering a world in mutation. Let's begin with the geodynamics of this period, meaning the internal movements of the Earth and the displacement of tectonic plates. In the Coniacian and Santonian, several major phenomena shaped the Earth's surface. The collision of the Caribbean island arcs with the Mexican margin, the first uplifts. That is, the progressive elevation of mountain ranges in the Andes, and their geomorphological effects deeply mark the landscape. Island arcs are alignments of volcanic islands formed along subduction zones, where one oceanic plate slides under another, usually continental, causing intense volcanic activity. In the case of the Caribbean arcs, this subduction gives rise to a chain of volcanic islands. Towards the end of the early Cretaceous and the beginning of the late Cretaceous, these arcs drifted due to tectonic movement, then converged towards the Mexican continental margin. Island collision, sometimes difficult to visualize, does not involve two continents, but a volcanic island arc coming into contact with a larger continent. When this arc strikes the Mexican margin, several local collisions cause the compression of sedimentary layers located between the two, generating folds, thrusts, and uplifts. In the Coniacian and Santonian, these repeated shocks modify the relief of North and Central America, reshaping the coasts and uplifting certain portions of the Earth's crust. The first episodic Andean uplift marks an initial stage in the formation of the Andes. Although the modern Cordillera is still far from existing, a gradual uplift begins as early as the Santonian, caused by the subduction of the oceanic plate under the South American block. This still modest relief results from tectonic compressions and the rise of magma deep down. Some segments rise above sea level, while others sink. This phase initiates the construction, step by step, of the imposing Andean chain. This geodynamics forms a determining backdrop. It influences the distribution of epirix seas. These shallow seas partially cover the continents and guide the migration routes of terrestrial fauna. Each collision generates a sediment influx. Compressed rocks disintegrate, feeding neighboring basins. These accumulation zones can foster marine life, or conversely, disrupt it if the turbidity or chemistry of the water changes too dramatically. The Coniacian slightly precedes the Santonian, with the boundary around 86 million years ago. Throughout the interval, tectonic activity intensifies. Major subduction zones, notably around the Pacific Plate and the American margins, sculpt a world in constant evolution. The movement of the Caribbean islands, combined with deformations in Central America, creates a dynamic landscape made of shoals, straits, volcanoes, and nutrient-rich marine basins, conducive to flourishing biodiversity. Despite tectonic upheavals, the Earth remains at that time a vast landscape of shallow waters covering portions of the continents. Marine vertebrates move freely between basins, and coastal dinosaurs take advantage of these wet zones to hunt and reproduce. Geodynamics plays a key role in influencing sea level. An active oceanic ridge produces more crust, thickening the ocean floor and raising the waters that invade the lands. Conversely, tectonic slowdowns or intense collisions can cause local sea level drops. While we focus here on Caribbean arc collision and Andean uplift, it is essential to remember that other simultaneous upheavals affect the planet, sometimes interacting. The result is a complex world, fragmented by seas, where species distribution evolves rapidly, guided by plate movements, the appearance of natural barriers, or land bridges. Now, let us address the climate of the Coniacian and Santonian, as well as the accompanying isotopic cycles, like that of stable oxygen. At this time, the Earth remains in a generally warm state, typical of the Cretaceous, without permanent ice caps at the poles. However, the analysis of marine fossils reveals a slight cooling trend, about 2 degrees Celsius, or 4 degrees, compared to the previous period. To understand this drop, it is necessary to recall that the Cretaceous is a greenhouse period with average temperatures higher than today. A drop of 2 degrees, or 4 degrees, may seem minor, but it affects ecosystem composition, species distribution, and the intensity of phenomena like cyclones. Researchers rely on isotopic analyses, notably the measurement of delta-18 oxygen, an indicator found in shells or marine skeletons. The higher its value, the more it suggests a decrease in water temperatures, or, in other cases, effects of evaporation or glaciation. In the Coniacian and Santonian, geochemical data, notably from fossils of inoceramids like argon, a large marine bivalve, confirm this slight thermal inflection. It is also detected in sediments from other regions of the world. Inoceramids are large bivalve mollusks with thick shells composed of several calcareous layers. Belonging to the family Inoceramidae, they are abundant in Cretaceous sediments and serve as paleontological markers for dating certain periods. The isotopic signals preserved in their shells reveal the ocean's chemistry at the time of their formation, allowing researchers to reconstruct temperature fluctuations and other environmental parameters. This slight global cooling influences the intensity of hurricanes. These storms formed above warm tropical waters. When ocean temperatures drop, even moderately, the frequency and strength of cyclones tend to decrease. Thus, in the Coniacian-Santonian, a slight decline in cyclonic activity is likely. However, the climate remains much warmer than today, and these phenomena continue to impact the coasts, redistributing sediments and affecting the most fragile marine species. No climate is static. Orbital oscillations related to Earth's orbital variations, such as eccentricity, obliquity, or precession, add to tectonic effects and carbon dioxide fluctuations to generate climate variations. Known as Milankovitch cycles, these astronomical periodicities probably also act during the Coniacian-Santonian, modulating the intensity of the observed cooling. In summary, the planet remains dominated by tropical to subtropical climates, but a slight shift towards cooler conditions is now observed. This change influences plant blooming, plankton productivity, and the distribution of fauna-seeking environments, neither too hot nor too dry. Earth remains green, dynamic, much warmer than today, but is beginning a slow cooling. Let us leave geology and climate to explore the terrestrial creatures of the Middle Late Cretaceous. In the plains, islands, or wetlands, a great variety of herbivores and predators evolved, illustrating the richness of this period. Titanosaurs are a family of quadrupedal sauropod dinosaurs with long necks and tails that widely colonized the continents during the Cretaceous. They are found in South America, Africa, Asia, and even in insular environments of Eastern Europe. During the Centonian, and more broadly between Coniacian and Centonian, their diversity increased. Some are gigantic, others smaller, depending on ecosystems and their isolation. Around 70 million years ago, at the beginning of the Campanian Maastrichtian, titanosaurs like Petrustitan hungaricus and Uriash kadici appeared in the Hatzeg region of Romania. At the time, this area corresponded to an insular environment, as Europe was partially submerged. On these islands, dinosaurs often underwent phenomena of dwarfism, or, in some cases, gigantism. Although these species belong to the very end of the Cretaceous, they may descend from lineages already present in the Coniacian-Centonian, having evolved in isolation. This scenario illustrates the complexity of biogeography. Geographical isolation shapes evolution. Recent research, notably from the University College London, confirms this hypothesis. Let us remain in the Middle-Late Cretaceous. Texas, then partially covered by the Western Interior Seaway, also hosted dinosaurs. Among them, Invictarchus armatus, a nodosaurian discovered in 2024 and dated to about 85 million years ago, between the Coniacian and the Centonian. This herbivorous dinosaur belongs to the family of ankylosaurs, known for their armored backs. Nodosaurians, a branch without a tail club, are distinguished by their powerful musculature and lateral spines. The name Invictarchus, invincible arc, perhaps evokes its robust shell or the absence of local predators. Well-preserved fossils, including osteoderms and postcranial skeleton, offer a rare opportunity to study its defensive morphology. Predators are not absent from this landscape. Alongside the large carnivores, there are more modest theropods, such as the dromaeosaurids, famous for their sickle-shaped claws. These agile, bipedal dinosaurs with a forward-leaning posture use their tails as a counterbalance. Often referred to as raptors, they already had well-developed feathers by the Coniacian-Centonian. For several decades, exceptional fossils discovered notably in China have confirmed that many dromaeosaurids were feathered. During that period, these feathers probably served to regulate temperature, attract mates, or signal social status. Some were likely colorful and complexly structured. The evolution of feathers in dromaeosaurids illustrates a trend of the Cretaceous, the progressive diversification of theropods into forms close to birds. Thus, we talk about avian dinosaurs, halfway between the large scaly predators and modern birds. The traditional image of entirely scaly dinosaurs has given way to a more nuanced vision, where the presence and density of feathers vary according to species and their environment. The plant framework of the Cretaceous sees the recent rise of flowering plants, or angiosperms, although conifers, ferns, and cycads still dominate many environments. One can imagine vast forests mixing giant ferns, conifers, and flowering plants, forming complex ecosystems. Titanosaurs there consume significant amounts of vegetation, while nodosaurians, equipped with stout jaws, eat tougher plants. We conclude our journey by diving into the oceans of the Coniacian and Centonian, where marine life is in full swing. Large reptiles, termed placeholders, after the gradual disappearance of ichthyosaurs in the mid-Cretaceous, inhabit the deep seas or swim in pelagic zones. Let's start with the polycotyledid plesiosaurs, Plesiosaurs are large marine reptiles with a broad body and 4 powerful flippers used for propulsion in the water. The polycotylids, in contrast, have a shorter neck and a robust jaw, ideal for catching fast prey like fish. Fossils dated to the Coniacian and Santonian reveal a morphology adapted to fast swimming. A streamlined body, pointed teeth, muscular flippers. They are imagined chasing fish schools or stalking cephalopods in the warm seas of the era. In 2025, researchers described a new fossil cephalopod from the group of plesiosaurs, provisionally named Kanaloa, discovered near ancient volcanic flows in Hawaii. The plesiosaurs, close to today's squids, are distinguished by their internal structure and hooks. Kanaloa possessed a thick belemnite guard, an internal piece comparable to the rostrum of belemnites, probably used to stabilize swimming and stiffen the body. Like modern squids, these animals could likely release an ink cloud for defense, though the composition of this ink remains speculative. This discovery suggests that volcanic environments of present-day Hawaii were already habitable for cephalopods and other pelagic life forms during the Santonian. This confirms the wide distribution of plesiosaurs in the Cretaceous oceans. Let's leave the cephalopods to observe a remarkable planktonic phenomenon of the Coniacian Santonian, the Vatnsnaueriaceae boom. This refers to a group of nanofossils, tiny calcareous algae, close to coccolithophorids, that lived in the upper layers of the ocean. They produced coccoliths, small calcium carbonate plates, which settled on the seabed after their death. These microfossils, in varied forms, disks, rings, stars, indicate a strong planktonic activity. The expansion of Vatnsnaueriaceae indicates a marine environment particularly favorable to the proliferation of these algae during this period. Why is there talk of a boom of the Vatnsnaueriaceae? Several hypotheses exist. The slight cooling of the climate, combined with still warm and nutrient-rich waters, could have favored their rise. The geographical configuration with inland seas and dynamic exchanges between basins may also have created ideal conditions, good light and constant nutrient supply. These nanofossils fossilize in large quantities, which makes them excellent biostratigraphic markers for dating rocks and assessing marine productivity. As they accumulate, their coccoliths form calcium carbonate-rich sediments, which can give rise to limestone rocks. Some well-known white cliffs are a direct legacy of this. Let us return to the polycotylid plesiosaurs swimming in these waters. They feed on fish, which themselves are fed by the various levels of the food chain, dominated at its base by the plankton. Thus, the proliferation of planktonic algae indirectly favors the abundance and size of large predators. This mechanism, observable throughout all eras, follows a simple principle. More plankton feeds more zooplankton, leading to more fish, which attracts predators like marine reptiles. Alongside the large marine reptiles, a multitude of mollusks, sea urchins, crustaceans, and microorganisms like foraminifera adapt to variations in temperature, salinity, and tectonic effects. The rise or fall in sea level, related to plate movements, alters the available surface for life. Some species take advantage of new coasts or marine passages, while others decline as their niches shrink. Overall, the Coniacian Santonian shows relative stability of marine fauna compared to other Cretaceous periods marked by severe anoxia episodes. However, certain basins likely experienced local hypoxia, a partial lack of oxygen limiting the presence of benthic macrofauna. During the Coniacian Santonian, mosasaurs, large marine lizards, begin to assert themselves. although they do not become truly dominant until the Campanian-Maastrichtian. Some genera already appear in the coniation formations, sharing the seas with polycotylid plesiosaurs and other reptiles. These waters host a diversity of predators, each occupying a niche. Mosasaurs, more massive and powerful, hunt large prey, while polycotylids, more agile, target medium-sized prey. To close this dive into the Coniation-Santonian seas, remember a lively environment marked by a very warm climate on the scale of our time, but slightly cooler than the rest of the Cretaceous. This nuance moderates ecosystems without causing a major crisis. Researchers are closely interested in these variations to understand the sensitivity of marine environments. Recent discoveries, such as the cephalopod Canaloa, show how studying these marine deposits continues to reveal a prehistoric world still full of mysteries. In summary, the Middle Upper Cretaceous is marked by significant changes. The collision of the Caribbean island arcs with the Mexican margin shapes the emerging lands, transforms coastal ecosystems, and opens migration corridors. Meanwhile, episodic Andean uplift begins the formation of the first reliefs, which will later give rise to the Great Andes mountain range. On land, the titanosaurs diversify rapidly, with some isolated on islands giving rise to dwarf forms towards the end of the Cretaceous. Nodosaurs like Invictarchus armatus thrive with their armor, while dromaeosaurids develop feathers, highlighting the importance of thermoregulation and visual display. The marine fauna of the Cretaceous is cosmopolitan. Polycotylid plesiosaurs swim in dispersed groups, plioteuthid like Canaloa populate the depths, and nanoplankton, especially the Watsonaueriaceae, experiences a major boom, reinforcing the base of the food chain. This journey into the Coniation and Santonian reminds us that studying the past is essential to understanding Earth's dynamics. Fossils, marine drilling, astrochronology, synchrotron tomography, and other modern techniques provide 1,000 clues about this ancient world. By connecting geodynamics, climate, and ecosystems, we reconstruct the complexity of the planet. Understanding the formation of the Andes, the convergence of island arcs, or how cooling moderated hurricanes helps draw modest parallels with current changes. Despite the temporal distance, tectonics, water circulation, climate, and life obey the same universal laws that science strives to illuminate. This part ends, but the geological history of the Cretaceous continues. The planet will experience more significant changes, disrupting biodiversity. But let's stay with this rich period, full of singularities, mysteries, and scientific advancements. Documentaries often describe these lost worlds as distant and fascinating ecosystems. The Coniation and Santonian well deserve this description. The ultimate segment of the Cretaceous covers the Campanian and Maastrichtian. These two stages mark the end of an era where dinosaurs thrived, inland seas expanded and then retreated, and landscapes progressively took the shape of the Tertiary period. To understand this period, we need to explore the distribution of continents, fluctuations in sea level, massive volcanic eruptions, and abundant life on land and sea. During the Campanian-Maastrichtian, many dinosaurs reached their peak, while signs emerged of an impending brutal end. It is a phase of intense geological and biological evolution, culminating with the Chicxulub impact 66 million years ago. For now, let's focus on these last tens of millions of years: transformations of landforms and seas, climatic variations, animal diversity, then the final sequence leading to the extinction of non-avian dinosaurs. The paleogeography of the Campanian and Maastrichtian is marked by a marine regression, meaning a gradual retreat of the seas compared to the continents. The vast western interior seaway, which split North America into two blocks, gradually closes. Once, over 1,000 kilometers, 621 miles wide, it connected the Gulf of Mexico to the Arctic Ocean. Towards the end of the Cretaceous, its sedimentary deposits give way to plains and marshlands rich in terrestrial life. Simultaneously, land connections multiply, notably between Europe and Asia, forming corridors for dinosaurs, warm-blooded animals, and other vertebrates to migrate. This narrowing of the continents creates natural bridges for species expansion, redistributing habitats and encouraging diversification. This marine retreat also influences the continental climate, often more contrasted than with extended oceans. The dried-up coasts see the emergence of new plant formations, while the reliefs rise, locally modifying precipitation. This complexity explains why Campanian Maastrichtian faunas vary regionally, while sharing a general trend of marine retreat. At the end of the Cretaceous, the climate shows a slight cooling trend, even though the Mesozoic remains generally warmer than today. Equatorial regions experienced average temperatures exceeding 30 degrees Celsius, while the poles, more temperate, hosted less dense conifer and fern forests. This cooling partly results from the configuration of the continents, the lowering of the sea level, and major volcanic episodes. The late Upper Cretaceous is marked by the Deccan eruptions in present-day Western India, series of successive eruptions releasing immense volumes of lava and gases, notably sulfur dioxide. This gas forms sulfate aerosols in the upper atmosphere, reflecting solar radiation and creating a planetary parasol effect. These phases, occurring around 67 to 66 million years ago, likely caused temporary coolings known as volcanic winters. Marine sediments reveal, through the delta, 34 sulfur isotope, a strong production of volcanic gases during this period. Despite this slight cooling, the Campanian Maastrichtian remains very different from the modern world, without large ice caps, with mild seasons, and significant humidity at low latitudes. This mix of factors, volcanic activity, marine regression, and continental reorganization, sets the stage for a rich biodiversity that we will now explore. On the lands of the Campanian and Maastrichtian, animal life is dominated by a wide diversity of dinosaurs, small reptiles, diversifying mammals, and numerous insects. The tyrannosaurids, at the top, reach their peak with Tyrannosaurus rex, an iconic figure. In 2024, a close relative, Tyrannosaurus macraensis, was discovered in New Mexico, showing distinct features in the skull and jaw. Among herbivores, hadrosaurids, or duck-billed dinosaurs, occupy various habitats, from wetlands to grasslands. Although modern prairies are absent, these herbivores feed on diverse vegetation thanks to their skulls, equipped with complex dental batteries and horned beaks suited for foraging. The diversification of dromaeosaurids, small to medium feathered theropods, marks this period. Dakotaraptor, an agile predator, likely hunted in packs. Its arms and tail bore feathers useful for balance, display, or thermoregulation. Meanwhile, mammals gained confidence, though less diversified than dinosaurs. Among them, multituberculates, small rat-like creatures, had teeth adapted for grinding seeds and insects. They lived in underbrush and forest edges, safe from predators. Let's now discover some remarkable findings on the terrestrial fauna of this era. A recent discovery in 2025 in the Gobi Desert, Mongolia, reveals an exceptional gelistid mammal. This group of Cretaceous therian mammals displays four traits of placentals. The fossils include an almost complete mandible, isolated teeth, and postcranial fragments. This small rodent-like animal had a powerful jaw, adapted to a diet mixing hard plants like seeds and small invertebrates. Studies on dental enamel using X-ray microtomography reveal specific microware linked to the grinding of tough food. This shows that late Cretaceous mammalian fauna already occupied diverse ecological niches. Furthermore, in India, a fossilized titanosaur egg was discovered. These large, long-necked sauropods with massive tails could weigh several tons or several thousand pounds. The analysis of the shell revealed biliverdin pigments, similar to those in some modern bird eggs. This coloration, still debated, suggests that some non-avian dinosaurs laid eggs of varying hues, useful for camouflage or thermal regulation of embryos. Ornithopod hadrosaurids, like Edmontosaurus in North America, show great adaptation to various environments, from floodplains to riverside forests. Armored dinosaurs, such as ankylosaurs, remain diverse, using their bony armor and sometimes their tail club for defense. The terrestrial fauna of this period remains dynamic, evolving despite the environmental and climate changes preceding the end of the Cretaceous. In the seas of the Campanian and Maastrichtian, despite retreating waters and reduced coastal zones, marine biodiversity remains rich. Large marine reptiles, notably mosasaurs, dominate the food chain. Emerging in the late Cretaceous, these predators could exceed 15 meters or 49 feet. Among them, Tylosaurus and Mosasaurus stand out with their powerful jaws and conical teeth. Their paddle-shaped tail and sturdy fins grant them great agility. They preyed on fish, cephalopods, seabirds, and other marine reptiles. Elasmobranchs, sharks, and rays also prosper, with species like Cretox sirena, nicknamed Ginsu shark for its very sharp teeth. Isotopic studies on Cretox sirena teeth indicate that they might have had warmer blood than the surrounding water, enhancing their predatory capabilities. Ammonites, shelled cephalopod mollusks, remain diverse, although some lineages are declining. Planktonic foraminifera, like the globotruncanids, thrive on the surface, constructing ornate calcareous shells. These microfossils are essential biostratigraphic markers for dating deposits from the end of the Cretaceous. Overall, marine life intertwines large predators, evolving invertebrates, and prolific microorganisms. This richness will soon be disrupted by the final crisis that will affect the entire planet. To delve deeper into the examination of these marine ecosystems, it is essential to underline that plankton dynamics, notably of calcareous algae, play a crucial role in the biological carbon pump. Coccolithophorids, unicellular algae producing small calcium carbonate plates, are a cornerstone of late Cretaceous food chains. Their massive accumulations through sedimentation form calcareous layers, such as those composing the famous chalk cliffs in Western Europe. By comparing them to planktonic foraminifera, one obtains a high-resolution reference of climate and sea level fluctuations. The microfossils of these organisms, analyzed under a scanning electron microscope, allow the identification of different species and the development of abundance curves related to environmental factors such as surface water temperature or nutrient supply. These data, cross-referenced with isotopic signatures found in their tests, show that despite cooling, many seas remain relatively warm, harboring tropical or subtropical biodiversity. In the northern areas, marine fauna adapts to cooler waters, yet still warmer than today. Long or medium-necked plesiosaurs coexist with increasingly dominant mosasaurs. Corals, especially in marginal reefs, persist in warm areas, forming impressive calcareous structures. Benthic invertebrates, such as bivalves and sea urchins, populate shallow sea floors. Fossils testify to strong predation pressure, prompting some prey to develop sturdier spines or escape strategies. Thus, the Campanian Maastrichtian Ocean is rich in adaptations but will soon be disrupted. The last events before the end of the Maastrichtian prepare Earth for one of the greatest extinctions in its history, the one marking the end of the Cretaceous, 66 million years ago. This extinction is linked to an asteroid impact on the Yucatan Peninsula, forming the Chicxulub crater. But before this collision, the stability of ecosystems was already fragile. Sea level fluctuations, Deccan eruptions, and continental reorganization disrupted food chains. Biodiversity varied, with local extinctions of ammonites and certain dinosaurs. Clay deposits rich in iridium, a rare metal, appear near the Cretaceous-Paleogene boundary, attesting to this impact. Iridium enrichment reaches about 9 parts per billion in the clays of Gubbio, Italy, a key discovery in the 1970s, supporting the extraterrestrial impact hypothesis. This signature is also found globally, notably in the Caribbean basin, indicating that a massive cloud of dust and debris invaded the atmosphere after the impact. Before the cataclysm, Deccan eruptions continued to release sulfur dioxide and other gases, accentuating short-term climate changes. Combined, these elements weakened ecosystems, reducing their ability to withstand a major planetary shock. When the several kilometers or miles across asteroid strikes Earth, a series of disasters unfold: intense heat, rock vaporization, then a colossal tsunami in the Gulf of Mexico and the Caribbean basin. Massive fires spread, fueled by incandescent debris falling from the sky. Thick clouds of dust and aerosols plunge the planet into extended darkness, reducing sunlight. Food chains collapse, affecting first animals dependent on photosynthesis, like marine filter feeders and terrestrial herbivores. The following months see a temperature drop, called impact winter, exacerbating the crisis. On land, non-avian dinosaurs are among the most severely affected. In the oceans, ammonites, resistant to many crises, become extinct for good. Mosasaurs, despite their dominance, also disappear. This anoxia in certain waters, combined with the decline in primary production, accelerates these losses. Although these subsequent events belong to the Paleogene, the final crisis brings a brutal end to the Cretaceous, sealing the fate of many species. We conclude here, at the moment when the meteorite strikes the Earth and the geological history turns the page. The Cretaceous fades away, giving way to a transformed world where new players, notably mammals, are ready to occupy the freed niches.